All right, we're in the back side of the notes, and now we're going to talk about topic 8.2 from your book, Arithmetic Sequences. So an arithmetic sequence I referenced in the first video is a sequence where the difference between consecutive terms is always constant. So in this example, 4, 7, 10, 13, 16, it's arithmetic because the constant difference is always 3. So another way of saying that is you could add 3 to the previous term to get the next term. All right, so example 1, which of the following sequences are arithmetic? So in letter A, so 5 plus 5 is 10, 10 plus 5 is 15, 15 plus 5 is 20. All right, so that is constant, and if we graph those points, they'd be linear. All right. For B, 1 plus 2 is 3, but 3 plus 2 is not 9. You might recognize this as we're multiplying by 3, but that makes it geometric, so not B. For C, 1 plus negative 3 is negative 2, but then 2 plus negative 3 is not 3. So it's not C. And then lastly, for D, let's see, 2 plus negative 3 or minus 3 is negative 1. All right, then we can add another negative 3 to that, and then add another negative 3 to that. So D is also arithmetic. When we think about an arithmetic sequence, this should really jump out at us as basically a pattern that we associate with linear functions. So if you think about when a linear function, we might say y is equal to mx plus b, where x is our independent variable and y, our output, is our dependent variable. We could write a sub n equals mn plus b, where n is just the number of terms. Kind of similar to how we did that last example on the first page, but that was geometric, and that's why we used exponential. All right, so the sum of the first terms, and this is pretty important. I'm going to put stars by this. The sum of the first n terms is another way of saying the partial sum of the sequence. So partial sum, and this is something you might just see in calculus. The partial sum is defined as n divided by 2 times a1 plus an. So the partial sum from the first term for the first n terms is going to be n divided by 2 times a1 plus an. All right, so let's go through and work these examples. So in example 2, we're asked to give a formula for the nth term of the sequence. So looking at our sequence, we can tell that it is arithmetic. I can see that I'm adding 3, adding 3, adding 3. So that constant addition of 3 is how I know it's arithmetic. So if I think about this as, sorry, I was losing my train of thought for a second. If I think about what term this is the first term, second term, third term, and fourth term. This plus 3 is like my rate of change. So that's like my slope. In other words, if I were making the analogy to this being a linear function. My y-intercept from a linear function is kind of like my 0th term. So I would need to know what term would come before negative 4 to make this happen. So negative 4 minus 3 would be negative 7. So even though negative 7 isn't part of the sequence, that's like what we might think of as the 0th term. 0th is not really a word, but it's kind of like our y-intercept. So when n equals 0, that's what our output would be, or that's what the number in our sequence would be. All right, so now we can put this together. A sub n is equal to our change, so 3 times what term it is, n, and then plus our b value, which is negative 7. So either plus negative 7 or just minus 7. All right, so what helps me is when I get my formula to test it and just make sure it works. So if this is the first 4 terms, let's test this by finding the 5th term, since we already know it should be 3 more than 5. So a sub 5 is 3 times 5 minus 7, or 15 minus 7, which is 8. That checks out because we expected that to be 5 plus 3, or 8 for the 5th term. All right, example 3. For example 3, we're going to find the sum of the first 40 terms. So this is, again, what we call a partial sum. Partial sum. All right, so the sum of the first 40 terms. So we're going to use the formula that we're given up here in the box and say that the sum of the first 40 terms is equal to 40 divided by 2 times, let's see, our first term, a sub 1, plus our 40th term, a sub 40. All right, so we're going to need to know what that 40th term is. And if you are like me, you're not going to want to sit here and do this, like add 2 40 times. You might just be able to reason about it. We could also figure out that 40th term by just coming up with, we could think about the 40th term by coming up with an explicit formula for it real fast and actually finding the 40th term that way, or that's one way we could do that. I just wanted to peek at, Miss Lawson left me some notes, and I don't want to take you down a path with too much work, so I just wanted to peek at her notes that she left for this. Okay, yeah, so it looks like, I'm not wrong, that we would need to actually come up with that 40th term. And in her notes, she also came up with the explicit formula for this sequence. So if we go 1, 3, 5, 7, if I think about that, I know my change, I'm adding 2 each time. So my change is, my m value is plus 2 that I'm adding 2. My 0th term would have to be -1 there. So my 0th term, I would work backwards. 1 minus 2 is -1. So I'm just finding that number that would come before 1 if the sequence went back that way. So to find the 40th term, I'm going to use a sub n is equal to 2n minus 1. And then when I plug that in, a sub 40 is equal to 2 times 40 minus 1. Or 80 minus 1. All right, so my 40th term is 79. Sorry, I had to adjust my camera for a minute. That's why it's bouncing. All right, so now we could fill this in. So we've got, again, the sum of the first 40 terms is going to be 40 over 2. We know that's 20, but I'm going to leave it like this for a minute. The first term plus the 40th term. Okay. So now we can go ahead and add those together. So we know that's 80, and it's going to be 20, 40 divided by 2, times 80. Oops, 20 times 80. Let's see, so I think we're going to get 1,600 if we do that correctly. So the sum of the first 40 terms should be 1,600. All right, on to example 4. In example 4, we're asked to find the sum of the first 12 terms defined by a sub n equals 4n plus 3. All right, so again, this is a partial sum. We'll talk about other sums later, but we're going to go back and use the same formula. So the sum of the first 12 terms, I'm going to just leave n in it right now, will be n over 2, the first term times the first term plus the last term in our sum. So we know by looking at this that we need our first and 12th term essentially. So in order to do that, I'm going to first do a sub 1 is 4 times 1 plus 3, or nope, sorry, I don't know why I just did 4 times 2. So 4 times 1 plus 3 is 4 plus 3, that's going to be 7. For a sub 12, that's going to be 4 times 12 plus 3, so 48 plus 3, 51. Okay, so when we do this, we're going to have the sum of the first 12 terms is equal to 12 over 2, which will be 6, times 7 plus 51. So 51 plus 7 is 58. So this basically becomes 6 times 58. And if I did that correctly, that should be 348. I noticed that in Miss Lawson's notes that she actually plugged in these two values instead of finding them first. She just kind of plugged them in here. You could do that too. I don't really see why it would matter. But if you have questions about that, feel free to ask her when she's back. I think you can go either way. You should get 348 if you did it correctly. Last but not least, example 5, the sum of the first 20 terms of the sequence. And now we are given a recursive pattern. Man, you could write this out. I want to say that I am tempted to, instead of writing this out, to just look at this, look at a few terms of the recursive pattern and write the explicit. And as I'm glancing over the notes she left me, that seems to be what she would do too. So let's try it that way. We already know our first term is 2. So if I want to think about my sequence, I've got a 2 to start with. To find my next term, I'm going to take my first term and add 5 to it. So to get a sub 3, it's just going to be 2 plus 5. So my next term should be 7. All right, then to get my next term, I'm going to take the previous term, so in this case now my 7, and add 5 to it, because this is like our previous term. So 7 plus 5 is 12. Then I'm going to just keep adding 5. 12 plus 5 is 17. All right, so I could do that 20 times, or I could just notice that this is an arithmetic sequence, and I'm adding 5 each time. All right, so for me to come up with the actual formula for the sequence, I know my change is going to be 5. I need that 0th term, if you will. This is my first, this is my second. I need to know what would have to be out here. So 2 minus 5 to go backwards is going to give me -3. So now -3 plus 5 is 2. All right. So if I want my explicit formula, it's going to be a sub n equals 5n minus 3. Now I can jump to that 20th term without having to repeat this sequence 20 times, or repeat the addition of 5, I should say. So my 20th term is going to be 5 times 20 minus 3, which is, what's that, 100 minus 3, so 97. Okay. So now when we do our partial sum, we're finding the sum of the first 20 terms. So 20 divided by 2. And that's going to be our first term, which is 2, not -3, because -3 is not actually part of our sequence. Our first term plus our 20th term, 97. So let's see, when I do this, 20 divided by 2 is 10. This becomes 10 times 99, which is 990. All right.